Yes, and in fact, we can also talk a little bit about that today. If people have questions regarding the when to use this tidyverse, when to use base R, I think that can cause some consternation. That can cause some potential trouble. So we can talk about it, about when to use what in terms of R versus the tidyverse. So some people have come and talked to us a little bit about that. If you do have further questions, we can do another session like this, or maybe a special section, a special additional section specifically devoted to kind of converting between the two or navigating between the two, since that can be a bit of trouble. And in the class, we don't really take a stance like you should do this or you should do this. We view them more as tools, and sometimes you'll want to pick up a hammer, but other times you'll want to pick up an electric power drill. And it's the same thing with these tools. Sometimes you want the base R, and sometimes you want the tidyverse, and it will be a case-by-case situation as to which one will be better and which one will be less optimal for any given scenario. So that is a bit of an introduction. Thank you to all those who are joining us virtually. Sorry you couldn't be here, but we're looking forward to having you back as soon as possible. We're going to first talk a little bit about string processing in R, because that was one of the things that people actually talked about. Last time we asked everyone, Andres wasn't here unfortunately, but we asked everyone, what are some of the skills you wanted to learn for the projects? And one of the skills was a little bit of text processing, and the exam also has a little bit of text processing. So therefore, we're going to do a little bit on that today because it's going to be important. Making big data has a whole module on this, so we go crazy there. We really put pedal to the metal, but this isn't that class, so we're not going to go totally pedal to the metal, but we're going to go maybe halfway there. So we have this won't really require any data, but any data that we're going to read into R, but we're going to work with some strings, and I'm going to try to go not too fast. I'm going to try to go a good speed, but let me know if there's anything that doesn't make sense, because that's actually a sign. If something doesn't make sense, that's a sign you should raise your hand and ask a question, or just interject at any point. We can talk about it. So we're going to talk a little bit about just defining strings, working with strings, because the question on the problem set about assassinations asks you to process the text about an assassination, and it asks you to do a bit of a string search in the text for certain words. So let's go through how you could do that. First, let's just define some strings. So here we've just defined a single string. It's a vector with a string entry, and that string entry is Joe Biden. But most of the time, we're not going to work with just one string. We're going to work with a whole vector of strings. So here we've defined this string here, which has 3 entries. So if we do, remember, length is the number of observations within the vector. The length is equal to 3. We can also do nchar to count the number of characters in each of the strings. So we get 9, 12, 9, 14. This can sometimes be useful when you're doing some web scraping, when you're doing some making big data curation that we'll discuss in the next course. But that's one thing you can do. So you can compute the number of characters. This is all just introductory material. So another thing that you can do with strings is pattern match. I don't think we've talked about this before, but if we have, I can go through this quicker. But sometimes you might want to basically pattern match. You have all this set of strings, and you want to find which strings talk about what kind of content, or which strings mention which countries, or which strings mention which president. So you might want to do a string search within the string for a particular pattern. So you specify the target pattern by basically going pattern equals whatever the pattern is, and then string is what you'll search in. So grepl, that's L stands for logical. So this is going to return a series of trues and falses. The trues are all the entries for which this string match is there. So the second string is it contains the word Biden. So that's why in the second position we see a true. Everywhere else we see a false. This is a string matching sort of protocol, and within there's a whole set of special ways of performing matches like this called regular expressions that we'll talk about in the next course. But right now we're just going to do sort of the introductory kind of matching exercises since it's relevant for the problem set. So that's basically how we would match to that string. Are there any questions about this or not yet? Yeah, question.
So if within each object we could find like the combination of characters Biden, so
I think so. Yeah. So you're saying exactly. So you have all these strings. You have three. You have a vector of street. Three strings here, and we're going to search for this combination of characters. We could search for We could basically search for combinations of characters like this, in which case you'd actually have two trues now because the word president has IDEN in it. So IDEN. So that would actually cause a match for Biden. So sometimes if you're not careful, you might overmatch or undermatch depending on how the text has been processed, which is one of the reasons why later on we'll talk about why it's often a good idea to make everything lowercase. So you can do that by going to lower. That basically puts everything into lowercase, which sometimes can be good, sometimes might be bad, but it's often good just to avoid issues regarding the beginning of sentences and capitalization differences. It can be good to do that. So if we did put everything in lowercase first, and then we tried to do this pattern match, we're actually going to get all falses now. False, false, false. Just falses everywhere because this is capitalized, but this is not capitalized now because we've converted it into lowercase. So to make a match, we'd have to put it in lowercase too. And now we'll get back to where we started. So this is how we would do kind of pattern matching within R. Yeah, good question. Other questions?
Can you explain what false, true, false means or how to interpret that?
Yeah, so this is grepl. We're basically going to look, we have our string. This isn't logical. This is just the different strings. But what we're going to do is we're going to ask ourselves, this line of code, line 17, what we're basically doing is we're looking into this string, and then let's just go back to this simpler version of it. We're looking into this string, and then we're asking, does the pattern Biden occur in the first string? And if the answer is no, it returns a false. The answer is no, so it returns a false. And then we're asking, does the pattern Biden occur in the second string? And we ask that question again, does it occur in the second string? And the answer now is yes. The pattern Biden matches with Biden. So the answer is true. And then we ask ourselves again, in the third position, does the string Biden occur within the string next president? And the answer is no. So it returns a false. So overall, when we put it all together, we get a false, true, false. Basically saying in the first entry, this pattern does not occur. In the second entry, the pattern does occur. And then in the third entry, the pattern doesn't occur. So if we just get rid of this B, now the pattern match isn't Biden, but just Iden. And when the pattern matches Iden, we get a different result because president in the third position, it contains the string Iden. Does that clarify? Very good. Other questions? Yeah, so this is going to be very useful when you're web scraping, when you're processing all the data, when you're doing the problem set. This stuff will come up, and Andres might talk about it, but maybe other things too. So we'll see. But yeah, question.
Just a quick clarifying question.
Yeah.
So if we're looking for a specific phrase, all we need to do is pattern equals Iden.
Yes.
Or whatever. Okay.
Yeah.
Then my next question is if we don't have, I guess, does R automatically categorize things of text as string, or do we need to do something to the data to make sure R interprets those objects correctly?
Yeah, good question. So the question is, does R automatically determine or specify something as a string? The answer is it can be very variable. So this is the source of a lot of bugs in quantitative research, and there are two ways that you can have bugs. So let's just write this down. Bug way one, or buggy trip up one. This can happen when you want something to be numeric, like 1, 2, 3. You want something to be numeric, but it's not numeric. So then you try to go like this, and you get a bunch of errors. So this is one way that you can get bugs with that. Or another way you can get bugs with that is if, let's just do 3 to 9 or something like that. Another way you can get bugs is if you go like this. So as factor 3 to 9, and you try to do that, you also get error messages. So the best way to fix this, I personally like to write a function that basically takes something that's factor or character and converts it into numeric. So you can go like function x as dot numeric as dot character x. So this is maybe a little bit too much details for now, but basically the idea is to take something that is for whatever reason in the wrong type and to convert over into the right type. So here we're taking something that might be factor and we're converting it into character, and then we're converting it into numeric so that we don't run up with that problem. So if you just load in a data set into R, sometimes what should be numbers are actually saved as factor variables. So if you do a survey, that survey has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and those will sometimes be automatically saved as factors, but you might want them to be numeric or put it into your regression. If that's the case, then you would process the data by converting it. Either you can convert it using this function, or you can convert it using your own techniques, but you need to convert it. That's the first thing I'd say. The second thing I'd say is if you do have factor variables, sometimes I believe these will usually be converted over. So if we just do as factor, I'm pretty sure that these will be, so even though this is a factor variable, so I guess we haven't really introduced factor variables. When I say the word factor variable, do people have an understanding of what I mean? Okay. People are saying we want more information about that. So the basic idea is there are several different kinds of data types. One of them is numeric. I think we all have a sense for what that is. That's just numbers. We also have integers. Which are related to numeric, similar sort of thing. You can apply addition and subtraction operations to numeric things and also integer sorts of things. We also have character types of variables. That's what we're working with now. We're working with character variables. And I think we have an understanding of that. It's just something like text. But sometimes we have a factor variable. A factor variable is related to the other things, but it's a little bit different too. So a factor variable is used when we're doing regressions and we want to have fixed effects. So if I have the state, if I have, I don't know, Texas, Wisconsin, Texas, Massachusetts or something, I might have in my data set a variable that looks like this. And in many cases, I want this to be represented like in a regression context as not as characters, but in the regression context, I want these to be converted into fixed effects. So in many cases, this will actually be saved as a factor variable, either by default or by your own intentionality, so that when you throw this into regression, 1 through 5, when you throw these into regression, it will actually give you a result. If you didn't have that as factor thing, it would cause failure, because it's going to automatically convert it, I guess, to factor. But nonetheless, we can't really run a regression with characters. Like, how would you run a regression with the word apple? It doesn't really make sense, at least in this context. But what we could do is we could create a series of binary indicators like we talked about with fixed effects, and that motivates why we would want a variable type called factor. We would want a variable type called factor so that we wouldn't always have to go as factor, as factor, as factor. Instead, we would just save the column in our data frame, or the entry in our data frame, as a factor type, and then when we use it in a regression context, it will automatically just assume that we're supposed to convert it into fixed effects or use fixed effects with that variable. So that's what a factor variable is. It's sort of it takes a little bit of practice getting used to it, but if we have a factor variable, the basic idea is I'm trying to think of an analogy. It's sort of, in a certain way, although what a factor variable does is, even though the input might be a string, we represent that string with a numerical mapping. That's the basic idea behind a factor variable, is essentially how I would say it. So we can actually do 1 times as factor. Well, I guess as not numeric. We can convert a factor variable into a numeric variable, and what will happen then is that we will sort of see the numerical mapping that's being implied here. So Massachusetts is getting a numerical value of 1, and Texas 2, and Wisconsin 3. within this numerical mapping. So it's being done alphabetically here, if I'm not mistaken. So the factor variable type is used when we want to represent kind of a certain class of things like states, and we want to have a numerical mapping underpinning that. Andres, do you want to add, or does anyone else, does that clarify? I'm not sure how clear that is.
I guess then my question is like, if I have a column of text, do I need to convert it to anything before I use any of like the strings?
Yeah, good question. So if we have a column of text, in general, I would want to do as.character to that, because then we're going to basically take the factor mapping and remove it, because when we're doing text processing, we don't want that factor mapping, we just want the raw text.
Okay.
So as.character will take the factor variable, if it's saved as factor, and it will coerce it into a text format or text type. And you might need to do that in the problem set, I don't remember exactly, but it's never a bad idea just to do this anyway, because it can save you from running into problems with this factor mapping business. Yeah, good question.
I can add to that usually like the read functions that we use, so read.csv, or if you're using the tidyverse read_csv, they will not read anything as factors.
Okay.
So if you're using one of those, or read Haven or something, read Stata, usually they will not load factors for you. If you're loading an R object, so an RDS on an R data, maybe someone saved their variable as a factor for some reason, and then you'll have to worry about it. So that's what I would say.
Yes, good points, good question. It is a little bit confusing at first, but the basic idea is we have these different types of data. Numeric and integer, I think those are easy to understand. Character, I think that's easy to understand. Factor are a little bit harder to understand, but hopefully we're getting a deeper level of knowledge about that too. And good point about pre-processing the data by converting it into a character using the as.character command. Okay, so now this is basically what we already talked about. And here, if there are no, this is just another thing. If there are no matches, we're just going to get, if we're searching for a pattern in which or for which there are no matches, we're just going to get 3 falses. So here we're searching for the pattern country, but there are no matches for that pattern, that string pattern, within the set of strings that we're looking in. And therefore, we get false, false, false. That's what we have there. And there are a few other functions which are just good to know. Sometimes we might want to find the index of where a particular term occurs. So we could do this grep function will return the index where the true is located. You could also do which grepl, and that will give you exactly the same answer. But one way to just write it in a shorter manner is just to do the grep function. There's no L here, whereas there is an L at the end of this. So these are 2 functions doing similar things that are all relevant to text processing. And that's why we're talking about them now, because text processing is something that everyone was bringing up regarding things that we wanted to learn more about, in addition to the problem set concerning this. So that's what we have there. Grep, we can also return the value for which there is a match. So if we have this string like this, sometimes we might want to return the value Joe Biden when we find the pattern matched with the word Biden. So we might want to return the entry that matches with that pattern. So this grep function can have this additional argument value, and when we say value equals true, this will return the value of the thing that we just matched. If there are no matches, so if we search for I don't know, apple tree or something, apple tree. In this case, there's going to be no matches, so the result of this is just a 0-dimensional thing. It's just basically empty. It's essentially null, or it's an empty vector. So this is what happens when there's no match. Okay. So that's that. I think that should be enough for people to do the problem set, if I'm not mistaken. But I have a few other things in this tutorial. For example, we might sometimes want to replace a string with another string. And in that case, if we wanted to replace next president with Steve and Jesse, we could do that with the gsub command. So gsub, we'll just take the next president string and return Steve and Jesse. Notice that we're only replacing the thing that we're matching. So if we instead just did president, then we'll have next Steve and Jesse instead of presidents, so it'll be a little bit different. So it'll just replace the full match. There are ways of replacing the whole thing on the basis of the match, but we'll talk about that in a minute. Here are just a few other things about how you make things lowercase, how do you make things uppercase. It's a good idea generally to make everything lowercase, since sometimes things might be capitalized and some not, and for many text analysis tasks, keeping lowercase is a good idea. And finally, this is how you would basically take the whole any string with a match to the word next, and just slotting in the name Stephen Jesse into that particular arrangement. So this would be what you're basically doing here. I'll break it down just to review. So here we have this string, and the string is this string of 3 things that we just constructed. And now we're looking for we're going to create a logical that's going to be true whenever we see a match to the pattern text. So it'll be false, false, true. And then when we subset the vector here with that, it's just going to return that last entry. So false, false, true. It just returns that third entry. That's how these text subsettings work within R. It's similar to how it will work in other things in the machine learning class that we'll talk about as well, but that is for another day in the spring of 2025. So that is what we do there. We can replace the entire string entry with Stephen Jesse, and that is something you may want to do. This is extremely useful. I can't tell you how many times I've done this exact line of code, just modified a little bit for countries. Because when you're trying to merge 2 data sets, there's not a really great way, and different data sets refer to different countries with different names. It's the source of a great amount of headaches in the political science community. And I know there are packages for dealing with that, but at the end of the day, for some data sets, we're just going to have to change names from like the Republic of Country X to just X to harmonize all the names between the different countries. So this is something that you'll often do, or you'll often need to do when you're merging data sets when there's no other unique identifier. This is just another word of warning, so to speak, about that. Okay, are there any questions about this? Are people feeling good about this or bad about this? Yeah, question.
When you did G sub pattern equals president instead of just next president, I think I got next Stephen Jesse instead of just Stephen Jesse.
Oh, like right here?
Yeah, but instead of next president for the pattern, I just put president.
Yeah. Oh, well, I think we actually need to rerun the code. Yeah, so that is expected behavior. So the G sub will just take, so we have here, this is our string, and G sub will just replace, it will find this pattern, and it will replace only that pattern with the new replacement. So here the pattern is president. So we're going to scan each of these strings, the first one, the second one, the third one, and we see the word president here. And whenever we see the word president, we're going to replace it with the term Stephen Jesse. And that is how we perform this replacement. So this is an example of a string substitution where whenever we see president, we're going to replace it with Stephen Jesse. And that's why when we run this code, it says next Stephen Jesse. Yeah. Yeah, so if we wanted to pattern match, or if we wanted to string substitute the whole thing, we could go like this, and now it's going to string substitute the whole term next president. Does that make sense?
Yeah, but does that have the same result in the next line of command that we did?
Oh, right here? Yeah, so right here, in this case, it doesn't matter which one you choose. Whether you choose next president or next or, or president, all of these 3 things, all of those 3 different ways of doing it will do the exact same thing, because anytime, all we're doing is we're looking for a match to next, and then we're basically going to replace the entire string with that match with Stephen Jesse. Same thing here, we're going to replace the entire string with that match, with the new term. So it's a slightly different logic. Instead of string substituting, it's a string. It's like an entire string replacement. So we're replacing that entry in the string based on this pattern match with the new thing that we define here. So it's sort of a stronger operation. The first thing is kind of local. You can think of it as being local. The second thing is more global, if you want to think about it as more global. Yeah, good question. Any other questions? Does this make people feel better about the problem set? I think the problem set talks about this. I think you're going to be looking up the term assassination or something like that in the problem set, which I think the problem set's a fun one, by the way. I hope you have fun with it. I think it's an interesting one, to say the least. Obviously, assassination is no light topic, but it's an interesting sort of intellectual exercise despite the gravity of the subject. And then I have a few other words here just about encodings. This is the last thing we'll talk about here. So in some cases, when you're dealing with data from disparate sources, perhaps data that's not always, let's say, English, but it could be another language, it could be Spanish, it could be French, it could be Italian, it could be Arabic, it could be Chinese, it could be Japanese. In many cases, these different languages use different encodings. An encoding is basically a way that your computer saves these characters. That's like a recipe for saying, what character should I display on the screen? We don't have too much time to talk about it, but the basic idea is you'll often want to use the UTF-8 encoding. So when you're working with string variables, it's never a bad idea to, at the beginning, going as.character, my text, and then in addition to that, going encoding to UTF-8. I don't have too much time to really go into the details of why you should do this, but it's often a good practice to convert all your encodings so that they're in the same sort of computer language. This can sometimes cause trouble if you don't do this. So it's good practice to do this, because otherwise there can be disastrous consequences, and that's never good. So those are just a few thoughts, a few reflections. Like I said, we talk more about this in making big data, and these sort of string substitution systems actually are really, really powerful, and we've just scratched the surface. There's a whole sort of language or whole sub-language within R of these substitutions. So if there are no further questions, I hope this was helpful to the problem set. Did this address, I think someone posted on Piazza to talk a little bit about this. Did this, hopefully this, yeah.
Yeah, I have a quick question. If I want to get everything into other format instead of UTF-8, should I just change UTF-8 to others to
Yeah, so there are encoding. There are a few different ways of doing this. One way is to use, and I haven't done this in a while, so I might not remember all the details, but sometimes what you'll want to do is basically, set the encoding to a value. So in this case, we can set the encoding to UTF-8, but in other cases, we might want to set something else. And there might not be a function built in for that encoding. So we would basically do encoding, my strings, and then we would give it the encoding. We might say give it the encoding Latin 1 or something like this. I will say this, for those of you who are working with non-Latin based languages, R does sometimes struggle mightily with that. So even just plotting characters in, let's say, so for this one project, we wanted to plot characters in Chinese on the R plot, and this caused us a great deal of problems. So there are some issues with that, and maybe Andres or maybe others have hints and tricks that we can post onto the Piazza about that, because it can really be trouble in terms of non-Latin languages. So just keep that in mind. If you're struggling with that, that's actually totally expected, and I probably spent days trying to work through some things related to that for various projects. So it's not something that's it's actually challenging within R to do that. R kind of assumes, at a very deep level, it assumes something about the encodings and about it's expecting Latin characters, and to change those basic assumptions can be involved. A good question. Other questions? Okay, so I think I will close this for now. And that was one of the questions. And I think you were asking about question 3 on the problem set. So let's actually just pull up question 3 on the problem set and talk about it. So, where is it? So, question 3. What was there a specific aspect of the question? Interpretation. Oh yeah, that's right. Okay, here it is. The solutions are there, but I'll be sure not to open the solutions one. We'll just open the other one. Alright, so. Okay. So yeah, we're going to talk about some of the things for this problem set today and also next time too. But the question is, interpret the results in light of the aforementioned assumptions. And we're basically trying to look at the distribution of quality scores before and after. And the previous question was about randomization. So yeah, this is actually something we haven't really talked about, but it's a little bit on causal inference, which I know you all are doing for your exam, for your scope and methods courses. So the basic idea behind experiments is that we want to somehow generate two groups, a treated group and a control group, and we want these two groups to be as similar as possible because that's going to allow us to make counterfactual comparisons. When we don't have an experiment, we have big problems. For example, countries which are democratic are very different than countries that are not democratic. Democratic countries cluster into certain regions. Democratic countries generally have a certain kind of, they have a certain historical trajectory. So democratic countries are very different than non-democratic countries. So we can't just say, look at democracies and compare them against non-democracies in terms of GDP growth to look at whether democracy promotes growth because of the fact that these two places are just very different. So what experiments do is they randomize people into the treatment group and randomize people into the control group. And this can sometimes cause what's called finite sample imbalance, where the treatment group and the control group, just by chance alone, are a little bit different. So you could imagine an experiment just with two people, person A and person B. Just by chance, or just if you have a man and a woman in the experiment and you just have two of them, by construction, 100% of the people in the treatment group are going to be men and 100% are going to be women. So when you try to do the analysis, you won't be able to say, is it due to the treatment or is it due to the fact that we're looking with men here and women there. So this is called imbalance. It's imbalance between the treatment group and the control group, and it can still occur even if you have randomization. So it's a problem with experimental design. As you get more and more observations, those sort of imbalances between these two groups get less and less and less pronounced, but it's still present, it's still operational. However, in many cases we can't randomize, so instead we actually use what are called natural experimental methods. Recently winning the Nobel Prize, I think it was a few years ago, the Nobel Prize today in economics was just announced as well. So we have the treatment group and the control group, and with the natural experiment, we basically, in one of the variants of these things, is we find a situation in the world where there's some important difference, and that important difference between some units and other units, although it wasn't randomly assigned, we can hypothesize the idea that it's as if randomly assigned. In other words, in this case, we have these leaders, and some of them are being assassinated. There are these assassination attempts. And the assassination attempt is either successful or it's a failure. And we might want to understand the effect of a successful assassination attempt on downstream effects, on like future political changes. So there's the successful attempt and there's the unsuccessful attempt. And in this question, we're asking ourselves, is this distinction between successful and unsuccessful attempts as if random? In other words, if successful attempts, if it's just random chance whether the bullet happens to pierce the heart or just miss the heart, if that is as if random, then we shouldn't see any differences on the previous data for the two different groups. The places that had successful attempts and the places that had unsuccessful attempts should look as similar as possible beforehand. And if that's true, we would expect that if that's true, then that's an indication that we're potentially in a world where this is kind of proxying a kind of randomized experiment where we have this thing happening and we can compare the successful and unsuccessful outcomes as a way to understand the causal effect. So when the interpretation is coming, the interpretation is going to say something like the successful coup attempts or the successful assassination attempts generally happened in richer countries or poor countries. Therefore, the natural experiment that we're trying to argue for is undermined. But if the two distributions look the same, then the idea that this is a natural experiment, we can use this in some kind of causal sense, that idea is strengthened. So that's kind of how you would approach the question. Any follow-ups, so I can talk more too?
No, that's good. I think it'll make more sense whenever we go over the bulk of the course.
Okay, yeah, so the basic idea is look at the pre-treatment covariates, and if you see something that looks like this, where let's just say that this is polity. If these are the failed attempts and these are the succeeding attempts, this would be on the pre-polity. This is an indication that the successful and the unsuccessful attempts happened in systematically different contexts. But if you see the two distributions look really similar to each other, then that would be an indication that this success versus unsuccess kind of natural experimental variable is potentially justified as if randomly assigned, because there are no systematic differences between the two groups.
Okay, yeah, that helps.
Yeah, good question. Yeah, thought.
I just had a question. Is the only comparison like skewness, or is another comparison like the variations between like the histogram? Like one has a much larger like variation as opposed to the other one. Would that cause problems too, or are we just looking at skew?
Good question. So any difference between the two distributions would potentially be a cause of concern. So if they look more skewed, or if one looks more variable, any difference would be potentially something to discuss. So ideally they would look exactly the same, but in lieu of that, then there might be differences. Yeah. Good question. Other questions? Other thoughts? Yeah. So that's for. Okay. Cool. So this will be hopefully an informative problem set. So there was another question to go through, like first differences models and fixed effects models, and I'll just talk a little bit about that. This is using the same tutorial data as last time. I updated it on the Piazza, so it's updated there, but we'll just talk a little bit about different kinds of time series models, and then we'll get started. Then we'll take a break maybe, and then we'll get started on hypothesis testing, since, yeah, it's the updated version. So,
The dependent data one?
yeah, dependent data, exactly. So first of all,
It looks
this,
like there's only the PDF for that one. That it's not on. Oh wait, no, I see it.
oh, it's there,
Got
okay.
it. Ooh.
Cool. So by the way, there are, in this file is information for how you would do cluster standard errors. Maybe I won't talk about that now, just in view of time, unless there's a lot of demand for it, since this is a democracy ultimately. But so we've talked a little bit about what a lagged dependent variable is. A lagged dependent variable model, basically we have the outcome, which here is GOP vote. So big picture context. We're trying to understand how the introduction of Fox News into the US media marketplace affected GOP vote share. And we're using a regression framework to try to attack that problem. And there are a few different ways we could do that. One of those ways would be to have a fixed effects model for each state. So this is a fixed effects model for each state, because we had those residuals that were clustering by state. So then we introduced fixed effects by state to try to account for all of the unobserved differences by state, to try to remove those systematic differences between all the residuals. And that's what we did last time. And we also did this lagged dependent variable model, where in the equation for the conditional expected value for GOP vote share 2000, we include in that formula the vote share from the previous election, which in this case was 1996. So this would be a fixed effects model that uses log of income, and that uses fixed effects for state, and that uses a lag dependent variable. So this sort of model I think is a reasonable choice. You're addressing the heterogeneity by state with the fixed effects. You are including the lag dependent variable, and those are all good things. So we could run a model that looks like that. We could also run a first differences model. There are many different kinds of first differences models, and there is a course at ICPSR on this. Maybe we could do a course in the department if people want to go wild with fixed effects models in addition to time series models. But the basic idea behind first differences models is what we're going to try to explain now isn't the level of something, but instead the differences. So previously we wanted to understand how do we predict the level of GOP vote share. We wanted to predict the level of the GOP vote share. but now we want to predict the change from one year to another year. So here our outcome is no longer going to be just the absolute vote share, but now it's going to be the change from 2000 from 1996 to 2000, and so that's the new outcome. If we change the outcome, we're predicting no longer the level of something, but now we're predicting the change in that thing. So it's a slightly different logic. So the idea is, before we were asking, does Fox News Access predict the value of the vote share in 2000, conditional on these other things? Now we're asking, does Fox News Access predict the change from one year to another year in terms of GOP vote share? And we can here include the change from the previous period as another predictor. So there, in the time series world, there are all these interesting connections between these different modeling approaches, and even between these approaches with something called diff and diff method. So there are all these interesting connections between these different things, but I would just think about it in terms of, what are you trying to predict? So here, we're actually trying to predict the change in something, not the absolute level. So this is this kind of burst differences framework, and we can analyze the results. So previously, let's just summarize these results. So previously, in the model with the lag dependent variable, first of all, our R square is much higher, because predicting next year's electoral returns using this year's electoral returns is a pretty easy thing to do on a relative basis. That's why the R square is really high. And that the coefficient on Fox News is negative and not significant with this model. So that's in the lag dependent variable model, we would reject, basically we would conclude that Fox News doesn't have a big association with the levels of GOP vote share in that election. When we have this other model that uses those first differences, we see that the R square is a lot lower. The R square is a lot lower because it's much harder to predict the changes in something than it is to predict the levels in that thing. For example, if I want to predict GDP in all the different countries of the world next year, a really good guess is the GDP this year. The R square on that prediction is going to be really high. But if instead I try to predict the GDP growth, that's a much harder task. It's much harder to predict growth than it is to predict levels. So that's why the R square in this model that uses a first differencing approach is so much less powerful. The R square is much lower. And if we look at the results here, in this case, it looks like the conclusions actually differ a lot. When we use this different approach, it turns out that Fox News, actually the conclusions are similar. Well, are they the same? I guess the Fox News indicator, let's think this through. The Fox News indicator is positive. And here, GOP vote share, this value is positive. The outcome is positive when the GOP vote share is growing. So with this alternative modeling strategy, we actually are finding that Fox News Access is predicting an increase in GOP vote share. Is predicting an increase in the GOP vote share. So with this first differencing approach, we're actually coming up with a different conclusion, hinting at the intricacies involved with time series analysis. Since there's so many ways to incorporate time into your model, and your results might differ, with one approach versus another approach. So in this case, you might want to analyze some of the regression statistics. You might want to look at the residuals. We might want to plot some of the results of the residuals and so forth to try to understand what's happening here. But that's just a bit of information on how you would approach this notion of first differences and things along those lines. So hopefully that helps. And if it doesn't, post a question on Piazza and we can further discuss and further get into the details there. But this is just how, in a real example, the choices of what you should and shouldn't do are actually quite large. You have a lot of leeway, and so therefore you should usually try to explain what you're doing very clearly and choose modeling approaches that are simple and explainable to your audience, because if you choose an approach that's overly complex, your audience might get lost, with the caveat being that you should always, do something that has theoretical justification too. So there are all these choices, and when you're in the research environment, you'll have to make those choices using certain heuristics, and we can talk about those heuristics when you face that question within your research. So these are just a few thoughts about burst differences, which I think someone had asked about on the Piazza. Hopefully this was helpful. If it doesn't help, send us another note on Piazza and we'll further clarify. Any follow-ups to that?
I asked it and this was helpful.
Okay, good. Sounds good. Thank you for asking it, and I'm glad that it could be of some use. Okay, so now let's take a bit of a break, and then we're going to get some really fun material. So we'll do a 4-minute break. We'll come back at around 1:55, and then we'll talk more. Yes.
Do you have time after class today so we can talk a little bit about your grading?
Yeah, that sounds good. Yeah, should be good. Should be good. Yeah, see you soon.
At least two. Or just like this brand.
I'll try to get the midterm to you by the start of this coming week, so that we can make sure that there are no issues or that nothing is missed.
That sounds great.
And then we can look it over that whole week, and then we'll release that next week.
That sounds great. We can prepare a TA session that's related.
Okay, that sounds good. In terms of this week, we're gonna start talking about hypothesis testing. So I think that's probably more important than the string stuff. But use your judgment. Whatever you do is good.
Alright, sounds good.
All right.
I'll have a Princess Bride one. There's dog.
I'll just pay this one.
I did see this was the. You were right now when it scopes us.
I know, I thought
looking at
I
it.
thought it should get mentioned since we were talking about this. And no one mentioned it. He was like,
I really want to slide down this bad, but.
are you guys done with your part of the PowerPoint so I can just send it?
Yeah.
I don't do it. There's no room. There's lots of pictures everywhere else. I'm fine, queens. I did change the title to the best group ever.
I was really content just to leave it, honestly. I think it'd be really funny and
Should
just
we?
add some brevity into the day.
I might put it back. I just changed it to police violence. But I do think it's good.
Oh, that's so and I already pulled a muscle a couple months ago, but it still doesn't really feel. And I'm out of icy hot patches. And I was gonna go grab some of my favorite stuff from the last day, but I tried. My lunch just made me really sad. My chicken wasn't very good. It wasn't good when I cooked it. And I was like, maybe putting it in my lunch was
Maybe it was a day thing.
I don't know what it was. I seasoned it so well. None of the seasonings, like, you shouldn't taste any of it. I put so much pepper. Oh my god, it was fine. I'm so sorry.
You're not allowed to get. You have to jump.
still deciding or something?
Yeah, so my sense is they approved the choices,
Oh, cool.
and
You know, like how
the issue
today's
is
Indigenous People Day. We don't say that.
3 weeks were given, like here are these options for 3 weeks when you can present to give job talk, but all the candidates said they want the last week, so there's a bit of congestion with the last week, but they're supposedly all interested and they're gonna come in and then we'll see what they say.
Excellent. When do you know when the first week is?
I don't, I think it's at the end of this month, but I'm not positive, but it's a good thought.
It's a little bit
No,
to
we'll
organize
show up to
everything.
Monday by Monday.
Exactly, I've been asking around about the candidates, so
Oh, you have.
just informal, just to get a sense of what people think.
Wait, so you had 2 or Harvard grades?
I thought it was a whole week.
Yeah, so I know them pretty well, but there's certain things that just to learn that we have learned, so we can talk about it at work next week. Yeah.
Oh, check the syllabus. Maybe I was looking at the 2020. Wouldn't that be the right one? We have. Still hiccuping. November 2nd. Yeah, we have November 20th.
Yeah, the syllabus,
Yeah, we don't have the Monday of Thanksgiving week off, right?
maybe not, I'm not sure. That could be a bug.
Cause on the like the UT official calendar, that's our fall break. Like that Monday.
Is it on the syllabus, is having class?
Yeah.
Okay, I can remove that, yeah, I must have.
I mean, no judgment, because I also thought that we had class that day. I was about to change my slide.
No. Yeah, we'll announce that. That's a good thought. Okay, cool. I think we should start again. We're a bit late. The break has gone too long. We must return to business. So, people were saying, thank you for informing me about this. On the syllabus, it says we're meeting on the Monday of Thanksgiving, but it turns out that that whole week is canceled due to the holiday, due to the Thanksgiving holiday. So we'll make that change on the syllabus, and we'll send out an announcement. So that whole week is off, 100%.
Thanksgiving.
Yeah.
So that November 20th through the 25th.
Yeah. So that week is 100% nixed. Okay, so we're going to talk now about crucial information, mission critical data. And the thing that we're going to talk about now is we're going to get into statistical inference. We've already talked a little bit about this notion of an estimator and how this estimator basically takes in data, examples, and it spits out an estimate of some quantity of interest. So we've already talked about that, how you have some estimator and it spits out an estimate of some quantity of interest. That quantity of interest is sometimes known as an estimand. It's the thing that you're truly trying to target. So that could be another term that you'll see thrown around. There's the true value, which is without a hat, let's say theta. And then there's the estimate, which has a hat. And then there's some way, some protocol, some algorithm, some recipe, if you will, of taking all of the observed data points, doing something to them, and spitting out an estimate. So the example that we've used is the example of trying to figure out what the true mean is from the true mean we posit the existence of this sort of superpopulation or this hypothetical construct where we have this random variable xi. We see all these examples of this random variable x1, x2, all the way up to xn, and we want to learn what's the true mean of that quantity or of that random variable from the sample. If we have a random sample from this distribution, knowing its mean might be important. Knowing its mean might tell us how much support there is for this policy or for this sort of intervention here or for that sort of intervention there. So we have this hypothetical construct of this true random variable that has some parameter associated with it, and we want to learn about that parameter using the data and using a particular estimator and using that estimator to learn something about that. We also talked about how this whole process has a certain amount of variability to it, and moreover, we talked about how this variability can be estimated from the data. The estimation variability can be estimated just like the quantity itself can be estimated. So this was like a second layer of calculation, and that was something we talked about as well. Today we're going to talk about a second side of the coin. So there's this notion here of understanding an estimate and an uncertainty estimate over the estimate. So that's one side of the coin, but there's another side of the coin that's related to something called hypothesis testing. And we're going to get more examples with this as we go. I think that conceptual material here can be challenging. So we're going to kind of break it up into these different stages. And today, in the remaining 20 or so minutes, I'm going to introduce to you, hopefully in a clear, accessible manner, this notion of a hypothesis test. Some of you have seen this, some of you have not seen this, but we're going to see it today if you haven't seen it already. And we're going to learn together. So there's a challenge problem here, which I'm going to skip over in the sake of time. It's a fun one, but there's no time. So instead, we're going to talk about hypothesis testing, and we have these 4 objectives: understanding the idea of a hypothesis test, and then understanding its assumptions, interpretation, and implementation. So these are the 4 aspects of our discussion for today. Let me just make sure that we're still recording. Yeah, it looks like the recording is still happening, so that's good. So let's just go back to the slides, and let's just talk a little bit about some questions that we would want to answer, questions related to quantitative social science. These are questions like, is the support for one political candidate distinguishable or different from that for another candidate? So is the support for the 2 candidates in this current presidential election, is the support meaningfully different between the 2? Or is my regression coefficient meaningfully different than 0? I fit a regression relating the level of democracy on the level of growth, and I want to understand, is this relationship in some sense distinguishable from 0, or is it not distinguishable from 0? This could lead to big consequences for our understanding of democracy and growth. We have other questions as well, like is my treatment effect meaningfully different than 0? If it is, maybe we should give people that treatment more often. So there are all these questions, and in general, we have this form. Given some data from the world, are my results, sort of broadly defined, quote, statistically significant? You've heard this notion, you've seen this notion, and today we're discussing this notion of statistical significance. And this is the general form of this kind of question. Given some data, what do we conclude from that data? And to do this in general, this notion of given some data, what do we conclude from it? We never think positively. We only think negatively. And what we mean by that is we're going to basically assume something, and then we're going to see if the conclusions from the data are consistent with that assumption or inconsistent. So you might have seen in the books or in the literature this notion of proof by contradiction. In the philosophy community, proof by contradiction is essentially doing exactly just that, but in a logical way. Assume assume X, then derive an absurd conclusion from X, therefore X cannot be true. This is known as proof by contradiction, and hypothesis testing is a data-driven version of this proof by contradiction idea, where we're going to assume something, assess the consequences, and then make a conclusion on the basis of that. There are some details that we're going to get more details in as we go. So think of this discussion almost like with satellite imagery. At first, the resolution might not be very great, but then as you zoom in, the resolution gets better and better. That's what we're doing today. We're getting a high-level overview, but as the course goes on, the resolution will get better, and our understanding together will be better. So these are just common questions that we want to answer, and hypothesis tests at least help us provide some answers under assumptions to the questions that were stated as mentioned before. So the general mechanics of this, as we just mentioned, are going to be very similar no matter what kind of hypothesis test you're doing. There's a certain skeletal structure to hypothesis tests that will hold in a lot of different settings, no matter whether you're doing parametric inference or non-parametric inference. And we've talked a little bit about that distinction, and we may talk about it more as we go. So this is the idea of hypothesis. We're first going to assume, and you might have seen this before, and it's good to review it if you have seen it before. So we're going to assume a null hypothesis. A null hypothesis, think of that as our baseline assumption. Like, based on this null hypothesis, we're going to then derive a conclusion of how likely an empirical result would be given that null hypothesis. So the basic idea is, I'm going to assume something, and then I'm going to use my data to derive a conclusion on the basis of that assumption, and then that conclusion will either be likely or unlikely. So we're going to ask ourselves, are the results likely under that assumption, or are they unlikely under that assumption? And the interpretation of these hypothesis tests is going to be very particular, very specific, very important. We're not going to ever accept the null hypothesis. We're just going to fail to reject it. So my null hypothesis might be that my regression coefficient is equal to 0. That might be my null hypothesis. And if the results of my experiment are likely under that null hypothesis assumption that the coefficient is 0, then what we're going to say is we do not reject the null hypothesis. The reason is the true coefficient could be 0.00001 or negative 0.000002. The true value, the true kind of parameter that I'm trying to understand more about could be really close to the null hypothesis value, and the conclusions of my analysis would be very, very similar depending on where exactly it is really close to that baseline value. And this is why we never accept the null hypothesis. We just either reject it or fail to reject it. So whenever you're doing like a formal hypothesis test, you're never going to say we accept the null hypothesis. Those words will be removed from your vocabulary. Instead, you're going to say we reject the null hypothesis, or we fail to reject the null hypothesis. So it's semantical, but it's semantical for a good reason, and the good reason is what I just mentioned, and we'll talk more about as we go. So those are a few thoughts. So that's what we mean. We don't reject, and on the other hand, we might sometimes reject. We might sometimes reject the null hypothesis if the empirical data that I see in the world are very unlikely under the null hypothesis. Then what we're going to do is we're going to, quote, reject the null hypothesis in favor of an alternative hypothesis. That doesn't mean the alternative hypothesis is true. All it means is that given the probabilistic assumptions of the setting, we are rejecting the null in preference for the alternative. So we're never accepting anything. That's how science works. Science works in a negative fashion. We're rejecting hypotheses that don't have evidence, but we don't ever know what the truth is. The truth is out there somewhere, and we're trying to get closer to it, but it's a hard task even just to get closer to it, and we never know if we're there or not. We might be living in a simulation where the things that we think are true are false, and who knows what could be happening. But on the basis of the data we have, we've rejected a lot of ideas on the basis of the sort of hypothesis testing, but we've never accepted anything. So that's just an important way that science works. And if you read these books on science philosophy, they're going to make a big deal about the negative nature of science. It never tells you what is, it only tells you what isn't. But the thing is, it's like a photograph, the negative of a photograph, or like you can sometimes learn more about what is by learning about what isn't, and that's why these hypothesis tests are important. So we're going to quantify this notion of likelihood, quote unquote, using what's called a quote unquote p-value, and the p-value cutoff between rejection and non-rejection in the social sciences is called the significance level, and there will be an interpretation of this as we go. But the significance level usually is denoted by this term alpha, and usually alpha is set to 0.05, and this 0.05, under the assumptions of the null hypothesis, will be interpreted as a probability. If the null hypothesis is not true, then this p-value is not a probability. So there's a subtle distinction there that we'll discuss. But so this is just a slide about p-values. A p-value is not the probability that the null hypothesis, which is denoted by this h subscript 0 or subscript naught, it's not the probability that the null hypothesis is false. You'll see this a lot. People will always say the null hypothesis is either true or it's false. It's either true or it's false. So in that sense, it's the p-value is not telling us anything about the probability it's true or the probability it's false. All we're saying is the following. This is the interpretation that you'll see. Assuming the null hypothesis, we would expect to see an observed test statistic as or more extreme and in p% of repeated experiments. So this is one interpretation of a p-value. We haven't really talked about a test statistic too much, but a test statistic is, if we go back to this slide, we have this notion of if the quote result is likely or if the quote result is unlikely. The slides are in slightly different order. I thought it made a little more sense to change them. Yeah, so this slide on p-values is I think it's towards the back of the slides that you have, but as I was looking, I thought it would be better to move them to the beginning. So the basic idea is that a test statistic is quantifying the result of the data analysis or of the experiment that I've derived. So when we see the word the result here, the result is basically going to be a number that will summarize the empirical data in some way. So this could be a mean, or this could be a difference in means. It could be a whole number of things, but the test statistic is essentially a kind of quantification of my data that I'm using in a hypothesis test. There might be multiple test statistics of interest, and in some situations, there are actually no limits on what your test statistic can be. Your test statistic can be anything, but there might be pros and cons to choosing different kinds of test statistics. So one of the things that we'll do as we go through this part of the course is we'll get more information about what are good test statistics and what are bad test statistics. More often than not, test statistics will involve means in variance estimates, but the basic idea is that that the p-value tells you about the relative plausibility of the null hypothesis to the alternative hypothesis, which is often denoted H1 or HA. And another thing to note is that these p-values will often be what's called asymptotic. So in many situations, the p-value will potentially have its desired properties only as the sample size gets bigger and bigger. So there are different kinds of hypothesis tests, and there are some differences here that we're talking a little bit about. But this is just a little bit on interpreting p-values. We'll go through this assumption, through this interpretation a little bit more as we go. But yeah, so here are p-values, and I guess it would be helpful to give a bit of an example. I know we don't have too much time. We have like 7 minutes. So I'm going to give an example, and I'm not going to have too much time to elaborate. But that's why we have next class, because in the next class, we're going to take these examples, and we're gonna dive into them in excruciating detail so that you never forget about hypothesis tests, you never forget how to interpret them, and it will be with you forever. So what are some examples? Okay, one example is that some mean of interest is equal to some constant. That's the null hypothesis. The null hypothesis is that the mean support for policy A is 0.5. That could be one null hypothesis. And there might be an alternative hypothesis that the mean support is not equal to that constant. This kind of test is called a two-sided test, where I'm specifying a parameter is equal to some value as my null hypothesis, and then my alternative hypothesis is the notion that the parameter is not equal to that value. This is a two-sided test because I'm not making a declaration about whether the alternative hypothesis is the true value is bigger than or less than. I'm saying it's just not equal to. It's not about directionality. There's no directionality here, which is why this is a two-sided test. Since if I have some parameter of interest, some mu of interest, you could think about being either to the left of it or to the right of it, bigger or smaller. And a two-sided test is just a test about are you equal to this thing, not about are you above this thing or below this thing. So that's why we have the term two-sided, because we're looking at both sides of this potential value. So this is the null hypothesis. This is the alternative hypothesis for two-sided tests. We have other kinds of tests, and here's some examples. We have other kinds of tests where we might, in some cases, have some theory for thinking that the alternative hypothesis of interest is that the true parameter might be below some threshold. So the support, I might have reason to think based on some theory that the level of support for some policy is less than some constant C. This is another kind of test called a one-sided test. It's called a one-sided test because now we're looking to one side of the parameter of interest. We're only looking for things, we're only considering the possibility in our alternative hypothesis that, in this case, that mu is less than some constant C. So that is the alternative sort of state of affairs that I'm going to use when I'm analyzing and comparing the null hypothesis versus the alternative hypothesis. So these are two kinds of tests. In general, I would say between 90 and 95 or even greater percent of empirical social science research will use one-sided tests. The reason for that is social science theory generally isn't strong enough to give us a strong sort of sense for whether the true parameter should be above or should be below this null hypothesis value. So in other words, because we often want to be more agnostic about whether the alternative should be specified in one direction or another direction, we in general will use two-sided tests. So when we're performing regression, when we're analyzing experimental results, when we're looking at survey data, we'll often, if not almost always, use two-sided tests. And we'll talk about further examples as to why that is in a minute. Another thing I would say is, so here are just some other examples. I guess here's an example. Well, these are just really examples of different kinds of null hypotheses and different kinds of alternative hypotheses in different sort of settings. So these are one-sided tests, these are two-sided tests, and here, this is just a classic terms regarding decision theory with regard to hypothesis tests. And like I said, this is just introduction, but it's important to talk a little bit about this. And I've listed out these types of error, type 1 error, type 2 error, and one of these two types of error is actually going to be more important in a certain sense, at least in the context of the hypothesis test than the other. So we have these type 1 errors and these type 2 errors. Type 1 errors, and it's just kind of wordy, so I'm just going to more or less read this. It's a little bit wordy, but type 1 errors are rejecting the null hypothesis when it's true. Okay, what does this mean? This basically means we are finding effects that aren't there. So if we reject usually the null hypothesis is some notion of the effect is 0 or the value is 0, the coefficient is 0. So usually the baseline null hypothesis is some statement about there not being an effect. And this is often considered to be a more serious problem than the other kind of error, because in the scientific philosophy community, there's this notion that it's worse if our literature is populated with wrong things than if our literature is just populated with fewer right things than it otherwise would be populated with. So the type 1 error rate is going to be controlled by the significance level of the test, that alpha that we talked about. So when we're doing hypothesis tests, we're actually going to come up with a whole machinery for controlling the type 1 error rate. The type 1 error rate is, in that sense, more central when it comes to the hypothesis testing literature. There's going to be this other kind of error as well, this type 2 error, which is, in a sense, the flip side. So failing to reject the null when it's actually false. So the idea here is my null hypothesis is the treatment has no effect, but the decision error is this null hypothesis is actually wrong, but on the basis of this procedure that I'm going to go through, I don't reject that incorrect null hypothesis. So this is false negative. The term false negative It's failing to find effects that are there, and this is not going to be controlled in any direct way by my hypothesis testing procedure. The hypothesis testing procedure, under its assumptions, will only speak to type 1 error. Type 2 error is a different sort of entity and will not be directly controlled by this decision protocol. So these are the two kinds of error. And the last thing we'll talk about today, and like I said, this is just a high-level overview, so if the details are sparse, that's because we haven't gone through them. This notion of power is the probability of a significant test rejecting the null hypothesis when the null hypothesis is false. So think of it like this. The power basically tells you if the power basically tells you something about your ability to find true effects when those true effects are actually there. So it's related to type 1 error, it's related to type 2 error. There are formulas relating some of these things in a more general way, but this is an overview to the different types of decision error, to the basic structure of hypothesis tests, since every hypothesis test that you'll see will have a very similar structure. And today we've gone through the skeleton of that structure, and next time we'll put some meat on the bones of it, and we'll talk about it hopefully in an accessible way so that it all makes sense. So that's all we have time for today, but we'll meet again on Wednesday, and we'll also meet again on Thursday for Andres' discussion section.